Hi friends. So let us continue from checking the continuity of functions. In the last video, I told you that I will be uploading two sums, which will be more fundamental in nature to understand the continuity of a function by giving two examples. One for continuity, which is a continuous function. The other example is meant for discontinuous function. So by seeing both examples, you'll be able to understand what is the continuity checking and discontinuity checking. Next, I would like to actually show you in the discontinuity or continuity, there are three types. Each type I will just show you here with a graphical representation. Let us see. Now, yeah, this discontinuities are of three types. One is called as the removable discontinuity. One is called as removable discontinuity. What does it mean? It means the graph or the function, whatever we are plotting, it will be progressing to some extent like this, and suddenly it will miss the data, and then again it will continue its journey. But you don't know what is the data here. This area is called as a discontinuity. This discontinuity is removable. Removable in the sense what? I will be approaching this discontinuity from this side, and the same discontinuity I'll approach from this side. So at this point, I will not directly approach because the function is not defined here. But what we do, we'll try to move towards this point from the left side and towards the same point from the right side, and then calculate the tendency of the function in from both the ends to what value they are converging. If that converging value is meeting directly by substituting in the function at that point, that means that point, let us say, for example, at x is equal to a, you want to check the continuity of this function. This is removable continuity, I am telling you. Now let us say I am traveling towards this discontinuity, which is there at particular point. Let us say x is equal to a. So this is the point. Now I have not defined the function at a. So I am checking the continuity of this function. So I will travel from this side. So limit x tends to a from negative direction, but means around the neighborhood. If this is a, I will be coming to a from this side and from this side. This is called traveling from left side. This is called left hand side limit. This is called as right hand side limit. Towards from both sides, I will be approaching a and then calculate f of a. Limit x tends to a plus f of a. One is LHL, other is called RHL. So both the values I'll compute. If both are, let us say, appearing to be converging to the same value, then I will record it. Next, I will directly go to the function and substitute this a. Directly limit x tends to a in the equation. If this is x square, I'll write a square like that. That value, if it is equal to, if this all these f of a's, one coming from the LHL, one coming from the RHL, and one coming from the direct substitution. So if all the three values are same, then this discontinuity can be removed. Understood? Now, one more thing. After this removable discontinuity, one more discontinuity we have to discuss. That is called as jump discontinuity. Jump discontinuity, as the name implies, the function will be jumping from one value to other. This discontinuity cannot be removed. It is difficult to remove. How does it look like? See, for example, I'm having a graph like this. Now a function will be going like this up to some value. Then from this, it will fall here and again go like this. You are observing now? So it means at this particular point, let us say x is equal to a, this will not have definition for this particular thing, but from here it will start. So this is called jump. Jump means the value is not recorded at this point. So we are supposed to find out anyway that discontinuity of the function. This is called as discontinuity of jump. That's called jump discontinuity. Another discontinuity is there. This is called infinite discontinuity. Infinite discontinuity means what? We don't know the other end. the function will be traveling towards this side. This is f of x, I'm writing all the time. Y-axis always write f of x. This is called x values, all are domain. X values are all domain values. F of x values are all output values or range values. You can write whatever way you wanted to write. So this function, you see what is happening. This is approaching towards, as the x domain values are increasing, this is going towards this side, whereas the output value is enormously increasing. This is approaching infinity this side. So in the negative side also, it will be, as you go from the domain side, negative side, again negative y-axis, it is increasing indefinitely up to infinity. So this is called as infinite discontinuity. This also we cannot remove. So now we learned three discontinuities. One is called a removable discontinuity, which we, by putting both LHL or HL, we made them equal. They appear to be converging, and then we said that it is a removable discontinuity. And jump discontinuity, we said that the data is missing. Suddenly there is a fall in the output. This cannot be repaired. We have to only avoid that particular value and then define the function here. Then other one we said infinite values, infinite discontinuity. Here also we should know at what value the function is going to infinity. So therefore that value, if we avoid in the function can be used. So jump discontinuity and infinite discontinuities can be used only by avoiding those inputs. Removable discontinuity, we can use it by observing the LHL and RHL endpoints. Now, let us go to two sums as I told you, and then understand as to how we can remove the discontinuity in a function. Let us see. I have taken, already I have calculated these values, because if I start doing now, it may take long time because calculator I used here. Now what is the sum now? Checking the continuity of f of x is equal to x square at x is equal to 1. Now what I did, equation first I understood. It is called f of x is equal to x square. It is a parabola that we know very well. Now this particular equation at x is equal to 1, they want to know. Generally we know, if you just draw here LHLC. Now what I'm doing, I'll draw this parabola for you. It looks like this. So let us say this is 1, and for 1 definitely it will be 1. Y coordinate also 1. So we know very clearly, if you put x is equal to 1, output will be 1. But we wanted to prove this, that if I approach this one from left hand side and right hand side, that is on the x-axis, this one I want to approach from right side and left side, and then see how the values are converging. Let us, I don't put the 1. I wanted to show that I don't want to put the 1 here for you, and then prove that this is converging. See, let us take x is equal to, starting from left hand side. Left hand side values will be below 1. So 0.5, 0.9 like that. Let us start very small neighborhood from 0.9 onwards. So I have taken here x 0.9. So what is f of x? It is x square. So 0.9 square. The value will become 0.81. So 0.99 you put now. Don't put x is equal to 1. So it will become 0.9801. Again, 999 you put. Like this, you can take so many values, but don't touch the 1. All these values, if you observe, 0.81, 0.9801, 99801, 999 like that. So finally, you can say that this value will converge to 1, because if you truncate it, what will be the final value of this one? It will be 1. So when I approached it from left hand side towards 1, without putting directly 1 now, I got a converged value towards 1. Again, if I come from the right hand side will become 1.1, 1.05, 1.0005, and finally 1.00005 or 001. We don't touch the 1. Here also we'll observe the output trending towards the 1. So both the LHL as well as the RHL values are trending to 1. Let us say straight away you put 1 in the equation. If you put directly 1, what happens? X square is equal to 1 square is equal to 1. So LHL value, RHL value, and then direct substitution value all became same. So this means that function is continuous. Even if there is a break at 1, for example, still the same methodology we can use and then get the answer. It is continuous. So removable discontinuities can be repaired like this. You have to come from the left side and right hand side towards the limit value, and then substitute the limit value in the direct equation, then see that whether it is continuous or not. Right now, in this case, it is continuous. Let us go to another example. In this example, yeah, yeah. In this example, I am having one more sum. This is actually called as a piecewise function. Piecewise means what? They defined the function x is less than or equal to 2 in one equation, x greater than 2 means another equation. So they are asking us to check whether this function is continuous at x is equal to 2 or not. We know now philosophy what to do. If a function has to be continuous at x is equal to 2, we have to approach the limit to 2 from left hand side and the right hand side around the 2. Then measure the values in each case, substitute properly in the equations given there, and then direct substitution we have to do again. See whether all the three are becoming equal or not. Let us take first one. First one is what? F of x is equal to x cube minus 2x plus 1, x less than or equal to 2. So now we are approaching the 2 from the left hand side. That means what? Below 2, less than 2. Less than 2 means I have to take the equation x cube minus 2x plus 1. 1.9. It is less than 2. So I am substituting in the top equation. If you directly substitute using the calculator, you will be getting 4.059, 1.95, 1.98. All these values without touching the 2, I have substituted. I have got here 4.059, 4.5148. Finally, it came to 4.99, and means it is merging as converging towards 5. Whereas second equation you take, it is called approaching 2 from the right side, above 2. So 2.1, 2.05, 2.01, like that I am coming. Above 2 means greater than 2. That time I should not use top equation. I should use the 3x minus 2 equation. In this equation, when I substituted the values of 2.1, easily you can see here, all values 4.3, 4.15. Finally, they are all coming to 4.003. Now you notice here, the RHL value at 2 and the LHL value at this near the 2, both are not same. Both are not coming same. It means LHL value is not equal to RHL value. So there is a discontinuity in the function. Then next one is direct substitution. It is at 2 they are asking. So at 2 means x is equal to 2. For x is equal to 2, we have to use the top equation, x cube minus 2x plus 1, directly substitute. That is coming to 5. So here what we are understanding is LHL value, even though it is converging towards 5, it is not equal to the RHL value, which is 4. Therefore, this function is discontinuous. So friends, this is how you can understand the continuity checking of a function. Don't go for the infinity checking and all. Infinity checkings means you have to avoid that value which is giving me infinity, because that cannot be repaired. So a function which can be repaired is removable function, and a function piecewise information if they give, you can use both the equations and get the functional response. Jump discontinued also cannot be repaired, but data can be collected and kept at each function or value. So friends, what I do, I'll conclude here. In my next class, I wanted to take up the important theorem that is called extreme value theorem. This theorem is very, very useful to check the differentiation or differentiability of a function, which I will explain very clearly in the next class. For today, I will conclude the class here, and please revise my previous classes if you have not followed, and any comments you can leave in the comment columns so that I will again repeat it if you want any further explanations. Thank you so much.